I'm going to present myself. So I'm Pierre-Olivier Autran. So I'm postdoc on 911 Beamline. So I did my PhD also on cultural heritage. So I'm a bit in the same field as you are. And today I'm going to present you. So I'm going to do a little bit of a tutorial on the powder diffraction phase identification. And so the presentation is going to be around 30 minutes. And with 15 to 30 minutes question, depending if you have questions. And so basically what we're going to focus on is like I'm going to do like a quick reminder on the basis of powder X-ray diffraction. Depends, I mean, you have all the different levels, so I guess it's good to have a little reminder. And then a part on the software called QualX2 and with the COD database, so which are the two phase identification tools we're going to use, and a quick example on how we can use them in the case of powder diffraction phase identification. So so basically, what is diffraction? So like a very quick thing is basically diffraction is you have an incident wave with an interfering object, and if the size of the object is the same as the incident wave wavelength, you have diffracted wave. So like a couple of like real examples where you have like like this waves on the left with like this blue interfering object, which is just this little slit in the middle, and then you have this diffracted waves that have like this like arc circle shapes. And then you can observe that even in nature with like waves and channels. So you see like you have these parallel waves and diffracted waves. It's a good way to illustrate this kind of effect, which I like. So X-ray diffraction is similar, it's just the scale is different. So the X-rays and so have the same wavelengths as the crystals features, so the lattice of the crystals, let's say. And basically what you observe when you have like this X-ray coming through this crystal is if you have like diffracted spots. So if it's a single crystal, we have this kind of spot features. And if we go to powder X-ray diffractions, it's like you have way more crystals, and you have that little crystals that are small relative to the size of the beam, and they have variable orientations. So instead of having spots, as you've seen just before, you have rings from these spots that are showing up. So, and you observe this kind of 2D image with rings. We've probably measured that a lot of time already. So how to get information out of this ring? So one way is basically you integrate azimutally, so across the rings, you integrate and you create a 1D diffraction pattern. So that's a very like a quick example here. Don't care about the densities, it's just to show the positions. And then like the positions of these peaks are following the Bragg law. So the sin of theta is like related, is proportional basically to the HKL distances, which is related to the structure of the crystal, and it's proportionate to the wavelength of the incoming beam. This is a very like basic reminder. So in reality, what you have is you observe things like this. So especially in cultural heritage, since you have a very wide range of phases with heterogeneous compounds, you have single crystals mixed with powders, with lots of things. So this is the kind of pattern you would observe. So on the left, it's a 2D diffraction pattern that was recorded at ID22. And on the right, it's a 1D diffraction pattern that was recorded at ID22 as well, but with the multi-analyzer stage. So usually you get from the 2D version to the 1D, but on ID22 you get directly to 1D because they are very fancy setup. So that's the data we're going to look at, basically. So what information can we get from this? So the first information we get from this 1D diffraction pattern is the peak position, basically. So the peak position is related to the size and the shape of the unit cell. So in this case, for example, the case I took is a cubic cell, so the angles alpha, beta, gamma are 90 degrees, but the lattice parameters A, B, C are just A, basically. So it's just a very simple, lattice. Peak intensities, there are positions and natures of the atoms in the unit cell. So depending on where the atoms are sitting, if they sit a bit further, like in a different way, then the unit cell can change the intensities a lot. So in this case, it's a very simple case, but it can be way more complex than that. In nature, it just depends on the type of atoms within the structure. And the peak width, this depends, okay, mostly on the instruments, let's say, but with a normal instrument, the difference is usually made of, depending on the size and strains of the crystallites that are making the powder. So if you have a nano texture, it's going to be like broader and so on, so things like this. So basically, we have, with all these sets of parameters, what you obtain is each crystal structure in your pattern will give its own set of peaks. So if it gives its own set of peaks, it means if we have measured them in the past, means if they are part of the database, we are able to identify them. So that's everything so that's the key point of what we're going to do, is like, if we have a good database, we are able to match the database to a measurement. So in practice, it can be very complicated. So this is an example of one sample I had from a powder found on in a Pompeii vessel. So it contains lots and lots of things with different, with variable sizes in crystal powder. But out of that, we are able to identify phases. So here I show an example of, I managed to identify most of the phases that are present there, not all of them. This is very complex, but you already have like 5. And so this is the result we hope to have doing this analysis, basically. So here you have like few like iron oxides, and so that's it. Okay, so so the software I'm going to present you today is called QualX2. So it's coupled with a database. So the software was developed by people from the University of Bari. So it's available on their website directly. So it's free. You don't need to pay anything, which is the big advantage of it, compared to other softwares, for example, that are like diffract, EVA, match mode, which are not always like free, and databases such as, for example, here the PDF2 to PDF4+, usually are very expensive. In this case, it's coupled to the crystallographic open database, which is free. So basically what this program does is just compare the peak positions, intensities to this COD database. So it's available on Windows, I think, probably not on Linux, but I guess most of you are using Windows, I hope. How it works, basically, so this is like a very big formula, but it's easier than it looks. So basically, the program calculates for a diffraction pattern a series of figure of merits for each phase it has in its database, basically. So it's going to calculate this number. It's a number that is between 0 and 1. So 0 means this phase is probably not in the diffraction pattern, and 1 is this phase is probably in the diffraction pattern. So how it calculates basically is it's giving coefficients based on 2 theta contributions, meaning it compares the 2 theta value of a calculated pattern and one with the experimental pattern. So the experimental, the phase in the experimental data. So it does this also for the intensities, and then it's like taking into account factors like some coefficients based on the intensity of the experimental data itself and on the database itself. So it gives like a different tuning possibilities. So the database itself is coupled to the software. So it's an open database that contains 440,000 entries that were put by people that are publishing. So it's not commercial. It's purely people add their structures in the database like this. So it contains like crystal structure of organic, inorganic, metal organics, and minerals. So it's very wide. So both of these are available at this link. So I'm going to send you the presentation to be able to get this link. You don't need to write anything. So to present what's the software features, I'm going to go quickly on what the software is capable of, and then I'll show you how we do all the processing in detail. So the first thing that you need to have is a 2-column file, or 3, depends if X, Y, X, Y, E, but like data with intensity and 2 theta. You cannot provide anything else than 2 theta. You cannot provide Q data, so you probably have to get your data in 2 theta. And then you have to give the wavelength. So the wavelength is usually provided by the calibration you made on your machine, or at PSRF, it's usually been my staff that's going to tell you the wavelength is 0.4 angstrom or something like that. So you input that when you start the program, basically. So then you have a toolbar, and the toolbar, basically you can select the 2 theta range you want to work with. You will have to subtract the background, so I'll move on quickly because this I'm going to show you later. Then you have a peak search option where you basically tell where the peaks should be. So it's based on threshold and sensitivity. So I'm going to show that later as well. 2 selection tools like this, all these buttons for search matching to set restraints. So the restraints is the most important part of the software. It's basically you can restrain it based on the chemical composition. So you can like say I want to look only at phases that contain this element, or you can say I want my phase not to contain this element. So you can restrain, and this is a very good way to shave your problem to have a very simpler problem. Then you can select database on the database, like some restraint if you want to have like certain types of sub-database, and or if you want to browse for a name, a specific name like calcite, quartz or something, or an entry that you know, like an entry in the database that you know. And then you can restrain also on like the cell properties, like cell parameters, the density, of the volume of the unit cell. That's it. And then you have like a bunch of navigation tool display tools. So a very quick example of the workflow. So basically, I imported here the diffraction pattern. So the first thing, so I provided the wavelengths already, and it gives me exactly this. So the first thing I'm going to do is I have to prepare the pattern for the software to be optimized, to be sure that it's not going to give me false positives, let's say. So the first thing is, if you have a very noisy pattern, which this is common, you have to smooth out all this noise to prevent the software to trigger peaks that are not intense enough and not part of the sensitivity of the algorithm, basically. So you have a few different ways you can set like different values of polynomial degrees and points in order to like optimize and to not shave off your peaks, but to get like to reduce the noise for the software to work correctly. Once you've done that, so you see here I've removed most of the noise I have, which is very good. Then you have to adjust the background. So here you see I have a bit of background. Most of the time background comes from the air or from the capillary that you measure in. So it gives you this like continuous signal that is spread all across the pattern. So what I do is I create a background. So here you see my background is pretty bad because I just created it. Then I can change the background depending on what I feel it's going to fit the best. So in my case here, the polynomial with like 20 coefficients works very good because you see I've like shaved off all the bumps that I have. It doesn't matter if it shaves a bit of the bottom of the peaks, because the peaks are still there and intensity is like is still okay. So that's how it does. You have many options. Some are better than others, like filter and polynomial are the two that works the best, I've experienced. So when you have that, you subtract your background, basically. So you ask to subtract, and then it just like removes the background. So this is very optimal, because then all the little peaks you see at the bottom of the diffraction pattern, I can filter them out all at once, basically. So we're going to see that right away. So now if we have this diffraction pattern, we could move on to the next step. And the next step is to tune basically what peaks I want to identify and what peaks I don't want to identify. So if you look at the first try here, so the default values, you see I am missing quite a few peaks. So by saying missing a few peaks, when a peak is detected by the software, you see this vertical black line that tells you, okay, there I found a peak. So you see like on the second very tall peak, after it, just you have a little one that has two little peaks hidden within. So these are not detected by the software, meaning they're missing. And if they're missing, you're less likely to be able to identify the phase that corresponds to these peaks. So that's the very important key part that you really have to take care of carefully so that you don't miss any peak. So to solve this problem, the first thing is, okay, maybe there is two parameters basically. You have the threshold intensity, so it's basically like a 0 to 1 threshold. Tells you every peak that is lower than 10 is just not existing for the software. So maybe I can reduce that. So if I reduce that, okay, maybe I reduced it too much now because I'm 0, so it detects any little pixel that is at the very bottom, which is just basically the noise that is just remaining from the, oh, sorry, what did I do? I did this. So it's basically the noise that is reduced from the background smoothing and background subtraction. So what I can do, but you see that now my two little peaks that we were looking at that are twin in the middle, now they're found, meaning it was the problem. So what I tune now is I'm going to increase the threshold and the intensity as well. And so now since I increase the threshold, I can tune the intensity to match the peak sunlight. And you see here, now all the peaks I want to be identified, which have like a meaningful value, are there. So they are there, meaning I will be able to input that in the software. So this is the key, the important step. If you manage to achieve that already, you're very in a good way to identify the phases. And you have to know that I'm zooming a lot, really a lot on the. So I just have very few counts over the thousands maybe I have on the large peak. So you have to zoom in the diffraction pattern to get these small peaks. Okay, so now we provided the list of peaks to the software. Now we can ask it to match all these peaks for us. So it takes usually a few seconds, maybe 1 minute, to look at the entire database. And then I get this. So then I get a list of candidates that are sorted by figure of merit, meaning the ones that are on top of the list are more likely to be in my experimental data. So if we can get a closer look at this, so this is the list I obtained. So if we look at this, you see you have some entries that are coming several times. So you see that gypsums is coming a few times. It's just because many people entered sometimes the same phase. So this you have to be have to guess which is the best. It's always a bit difficult, but usually it's okay. Here I can clearly see that I have a trend it wants me to get gypsum. Some of the compounds, they don't have a name because some people didn't enter the name when they entered their phase in the database. So this is sometimes a problem. But basically, once you have your own set of cards, you can always recognize the number. So here they are like gypsum, some I prefer to use, and so this is not much of a problem. So what I'm going to do now is basically restrain my search match. So if I feel that I have too many results, I can tune to cut off the figure of merit to a value that is higher so that I don't get all the ones that have a very low figure of merit. This is going to give me a lower number of entries, and sometimes it helps to sort out all the phases that I'm not interested in. Then, depending on my sample, and this is very important, I can tune the importance of the 2 theta or intensity values. I explain it. So if you have a single crystal, for example, you know that maybe the intensity is going to be wrong because single crystals, they give intensities that sometimes very high, sometimes very low. So maybe you're going to reduce the impact on the figure of merit of the intensity and increase maybe the 2 theta value because you know that your single crystal is good, it's going to match the correct lattice parameter. And then on the other way, if you have a phase that you really know it's a very good powder, but maybe the temperature as you measured at which you measured is higher, it's like 100 degrees. Maybe the 2 theta values are going to be shifted, so it's going to be less sensitive to that, but more to the intensity. So these are two cases. And then you can tune the phases parameter. So it's going to look for, if you have one phase, it's going to try to get just focus on only the peaks, assuming that it is the peaks that are in diffraction patterns corresponds to only one phase. And if you have multiple, it's going to try to match more phases, basically. That's basically it. And then what is extremely important is to restrain, of course. So if you're sure about an element that you have in at least one phase, you can already tell, look at just the phases that contain this element. So this can be helpful, for example, if you do fluorescence, and you're sure that you have a certain element in your sample. You can start as a first guess at saying, look at the phases that contains, for example, lead. And then it's going to output you, sort out still by figure of merit, but outputs only the phases that contain lead. So this helps also to sort out what you have. And then you can also do the opposite. It's like you can, for example, restrain and say, okay, I'm looking at a cultivator sample. I probably don't have many lanthanides and actinides, so I can just like say, don't give me the one that contains these elements. This is also a key point. So you can also like, okay, as I said, you can also like look for specific names and entry numbers. So you can load like entry numbers as like just you type them and then you load them and then you have like a let's say like a priori on your sample. So once you have done that, so you started to like accept phases. So what you do when you feel that you have a good phase, you click on accept, the little like tick on the right of the software page, and one by one, as soon as you accept one, it's going to remove the peaks from the accepted phase that you assume that correspond to the phase, and it's going to look just at the peaks that are remaining that were not attributed to this phase, basically. So one by one, you'll see your results are going to be refined, because the more you click, the more you accept phase, and then it's going to look deeper and give more importance to the phase that are remaining and were not identified. That's why you go down and down now. So here in my case, I identified like 6 phases. So you see it's not, there are more than 6 for sure, because some were not identified. So this can be explained, sometimes not being able to identify phase can be explained for a couple of reasons. For example, you're missing the entry in the database because the database never had this phase before, or no one put it in the way that the phase that you had because it was unknown or because it was not well put. And also it can be the way that sometimes if 2 peaks are very close one to each other, it can use the wrong one and like trick you into thinking I identified the 2 and it just got 1. Or also sometimes having single crystals. If you have like a single crystal that gives you just 1 peak because the orientation was not good, and then you can have issues. So, but it depends. It's really related to the type of samples you want to analyze. And also like having very minor, extremely minor phases is a bit more challenging. You need to look very much in detail. Okay. So like a few things about the software features. So every time you identify a phase, you can basically look at the card of the phase. So you can grab information about this phase, like the reference of the paper that it's coming from, all the lattice parameters, the value of the DHKLs, the reflections, and the 2 theta values. And you can grab directly the CIF file associated to this card, so that you could input it later in other softwares, like for read verifiers, for example. Okay, so in my case, so the final results, so identifies like 6 phases. I'm missing 1 in the list and left. So that's kind of the final result I get. So what's the difficult part of all this process? So basically, the most difficult part is first having good data. So having good data means like having a trying to minimize the noise compared like to maximize to minimize the noise basically, and if you can get higher resolution. So for example, ID22 gives one of the best sets of data you can ever get, because the resolution is so high that the peaks are not overlapping, meaning the software is less likely to confuse itself into thinking there is just one peak and actually there is two. So this is a very, very nice advantage for this kind of work. If you want to identify phase and you have high resolution data, this is really, really an advantage. Then getting good set of restraints based on the sample a priori. So it's like if you can get information based on your sample before trying to do this process, saying like you expect certain phases, you expect certain elements. This is difficult to get sometimes, but it's very helpful. Then make a proper pattern preparation. So like do this correct background abstraction, smoothing, and all these things. So if you do it correctly, this is sometimes difficult depending on the case. And also, by experience, you get also a minimum sense of what is realistically possible. Is like maybe you won't find uranium everywhere, or even if the software tells you it could be, it's probably not the case because you know what your sample is made of. And then practicing is helping to sort all these problems. Okay. So after this, the next step for you is probably going to be, I guess, to refine the model structural model for the diffraction pattern. And then this, I'm not talking about it, but this is kind of the step that everyone goes through then, is to use like full profitable GSAS, to try to do a real refinement to get the values of the percentage of each phase, like the quantification of each phase. So for example, in this case, I present on the talk, it's very difficult still because you see like it's lost in the crystal, and I kind of did a roughly good job, but it's very, very difficult when you turn to this kind of software. But I guess this is everything you need to know. So that's it. So I guess so that's the end of the presentation. So I will send you the presentation of this presentation. And I have also 6 exercises with real data that I measured myself, or that my colleague measured, on lab machines, or on, for example, ID22 data. So each exercise has like an information about what the sample appearance is, and what the diffraction. There is a diffraction pattern, and there is also the solution of it in the format of the software. So if you have any questions, I guess you can ask it now, and then you could ask me any question later on by email, or any question related to these exercises if you're doing them. And that's about it. Thanks for your attention.